Okay. So Mass 10 went well, I hope. Okay. Let's begin. We're in lecture 32, and we are about to start what I would argue is probably the trickiest topic in the class, which is the theory of influence lines and the introduction of the Muller-Breslau principle. That'll all make sense as we get into the lecture today. But I do want to mention a couple things on housekeeping. So I'll try and get your exam graded by Monday because I'm going to take them home this weekend. The attendance grades, I'll have those updated by the end of the week. But I really want to talk about this box right here. So your project is due in 2 weeks, okay? So if you haven't started it, I would consider probably taking a look at it. But I have 2 pieces of advice. The first thing is that if you have not yet watched the Lecture 13 recording where I go through the project, I would do that, and I would do that before you start taking a nosedive into all of the work, because there's a lot of tips and tricks that I throw in that lecture to maybe make your life a little easier on picking your first round of members, on picking your on how to iterate and do that quickly. The other thing that I'll mention is that I recorded a video a couple years ago, and it's only like 5 or 6 minutes long, and it's on the Excel function called VLOOKUP, okay? I would take a look at that, okay? Because what you're going to have to do is switch between members in order to iterate your members, and I show you a way of doing that very quickly in Excel, okay? And it's not hard, it's really straightforward, and so I would take a look at that, okay, before you start nosediving into it. And I think there's a couple of you that have already started to look at it, and I think for every one of them I said, did you watch Lecture 13? And they all said, it's been a while. I said, well, watch it again, and they watched and went, oh, okay. So if you watch Lecture 13 and watch this, I think it'll make your life a little easier. Okay? Sound good? Okay. All right. So today what we're going to do is we're going to start, again, what I would argue is probably the trickiest topic in the class. Okay? And that's the theory of influence lines. Okay? And to begin my discussion of this, I would like first off to talk about what I have here on the board, and I'm just making some stuff up here, so there's nothing here that's like anything to write home to the bank or write home about. You don't even need to jot this down. You know, today's one of those days where I want you to just sort of, relax, shake it off, and just be prepared for a new idea. Okay? So today we're all just gonna, be ready. It's gonna be new. Okay? Now, I want to begin by discussing this, okay? Now, this is, for the most part, I don't want to say a challenging problem, but it's a problem. We've handled problems like this in this class so far, right? Things like constructing the shear diagrams, constructing the moment diagrams, constructing the support reactions, okay? Or computing the support reactions. So I want you to, in your mind's eye, I want you to imagine that process. So if I asked you to say, okay, if I asked you to construct the moment diagram, think about all the steps that you need to do. Just think about it, okay? So we've got a hinge, so we need to cut a section to get some reactions. We need to write some equations of equilibrium, compute the rest of the reactions, and then draw the shear diagram, area under the shear diagram to get the moment diagram. Just think that through, okay? Think that process through, okay? Now, I'm going to ask you this, okay? Do it again, okay? Do it again, but I changed one of the loads. Now think it through. That's an entirely different problem, isn't it? It's an entirely different problem. New reactions, new shear diagram, new moment diagram. I just have made the whole problem entirely different, okay? By just changing a load, by moving a load, right? It's different, right? So I want to talk about that. I want to talk about the possibility that loads move, okay? Up until now, we have only dealt with stationary loading. I give you a problem, I give you the loads, you do the analysis. What happens if the loads move, okay? If we change the position of the loads on the structure, we have to repeat the entire analysis from scratch. And when do we ever see that in the real world? In a bridge, right? Bridges, the loads move, okay? So whenever we have moving loads, I want to ask 2 questions, okay? Can we develop a tool to help us analyze a structure that is subjected to loads that move, okay? What happens if the loads move? How do we handle that, okay? But the second question is, can that tool help us design, okay? And to get more specifically, if I have a structure, if I have, let's just say, a very simple structure, and I have a load, where do I put that load to generate the absolute worst case response in that beam? So the largest moment, the largest shear, the biggest reactions, okay? And I think that we would all agree that that would be very important if we were worried about design, right? Because we want to design for the worst case scenario. Make sense? All right, well, we have that tool, and the name of that tool is an influence line, okay? All right, so let's talk about influence lines. Now, before I go on to the next slide, I want to say something. I say this every time. I just want to make sure we're clear, okay? Influence lines are not shear diagrams or moment diagrams, okay? I'm going to say it again. Influence lines are not shear diagrams or moment diagrams. You know what? I'm going to say it a third time. Influence lines are not shear diagrams or moment diagrams. They look a lot like them though, okay? But I want you to know they're not the same thing. If we want to get technical, they're kind of inverses of shear and moment diagrams. But we'll get to that a little bit later. Okay, let's define an influence line. Okay, what is an influence line? It is a diagram that we use to assess moving loads. Okay, now the way that it works is the first thing that we have to do in order to construct an influence line is we have to identify a point of interest, okay? So whenever we're drawing influence lines, we're not really drawing influence lines for the entire structure. We're picking a specific spot on that structure and we're saying, okay, that's what we're interested in as the loads move. And so that point of interest could be support reactions. So for example, I could draw the influence line for the reaction here or the reaction here. I could draw an influence line for the shear right there, or I could draw the influence line for the moment right there, okay? And so that might beg the question, well, how many points do you need to pick? And we'll talk about that later. But for the sake of discussion, let's just say we picked a point of interest and we're going to draw an influence line. What we then do is we take that structure and we subject it to a moving load, and the load that we choose is a unit load. So you can think of it as one kit, but really it's just like a load of one. And we take this point load of one and we move it across the structure. And as we move it across the structure, we record the response that we're interested in and we plot it. And that plot is your influence line, okay? So one thing I'll mention is that as we go through the next few lectures, as we're constructing influence lines on homeworks and exams, I want you to be clear that that definition is the fundamental definition for an influence line. So it can serve as a gut check for what you're doing, okay? So to explain, I want to do a very basic example, okay? So I have here on the screen and here on the board, I have a simply supported beam, okay? It is 80 foot long, okay? So I have two reactions here. We have this support A and support B, and we're going to call this the reaction at B, and we're going to call this the reaction at A, okay? And what I'm going to do is we are together going to construct the influence line. The influence line, I'm getting ahead of myself, for the reaction at Y, or the reaction at A, okay, the vertical reaction at A. So what that means is that we are going to take this structure and we are going to subject it to a moving load, okay, and we are going to record the reaction at A as that load moves, okay? Everybody with me so far? Okay, I'm going to give everybody a sec to jot down where we're at, and then I want to eyes up here because I want everybody to pay attention to what we're doing. So I'll give everybody a sec to get caught up. With me so far? Okay, let me ask you a question. So let's start basic, okay? So here's the beam, okay? Let's say I put a load right here in the middle, and let's call it 1.0. If you want, you can think of it as one kit. It's really just a unit load, but we'll leave one kit there for the sake of discussion. If I put a load right smack dab in the middle of the beam, so this is 40 feet. If I put a load right smack dab in the middle of the beam, what is the reaction at A? 0.5 or 1/2, right? Okay, so what I'm going to do, so watch this. Where the load is, I'm going to come down here and I'm going to plot a point and we're going to say that's 1/2. Okay, with me so far? All right, now we're going to move the load. So now we're going to take this load and we're going to move it. So now let's put the load, I don't know, right here. If I put the load right there, what is the reaction at A? 0, right? So what I'm going to do is right here, I'm going to plot a big old goose egg, okay? Because what I'm saying is that what this point is the reaction here when the load's right there. So it's almost like I'm keeping my eye fixed. This is my point of interest, and then as the load moves, the point that I plot is the reaction right here, okay? So just to make sure we're all on the same page, what happens if I put the load right there? 1. So would you agree with me that that right there would be if I did it everywhere, right? That's everywhere. Ladies and gentlemen, this is the influence line for the reaction at A. That's your first influence line, okay? As the load moves, so let's just sort of digest what's going on here. As the load, so the load, when the load starts here, we have a really high response, right? As the load is here, A is 1. But as the load moves away from A, the reaction at A gets smaller. Like, does that make sense conceptually? I mean, yeah, as the load gets further away from the point of interest, that reaction is going to get smaller, okay? The distribution is linear. This is a line, right? At x equals 0, this is 1. At x equals 40, this is a half. At x equals 80, it's 0. That's a line, okay? There's a reason we call them influence lines, okay? All right? For statically determinate structures, this box is really important. For statically determinate structures, influence lines are lines, okay? So if you catch yourself on homework or on an exam and you're drawing an influence line for a determinate structure and you're drawing curves, I want you to take your hand and do that. You're doing something wrong, okay? Influence lines for determinate structures are lines, okay? Now, let's have ourselves a little pop quiz. Can somebody describe to me what they think the influence line for the reaction at B looks like? The other way, right? That's exactly right. See? Okay. So the influence line for the reaction at B would do that, right? Okay. So far, so good, right? This isn't too bad, right? Okay. Now, what I want to show you is a process for constructing influence lines for structures that are a little more complicated, maybe for something like that, okay? Now, if you remember when we did shear and moment diagrams, so let's talk about shear and moment diagrams a little bit. The very first thing that we learned how to do is cut a section, get the shear and moment here. Cut a section, get the shear and moment here. Cut a section, you get the shear and moment here. And then we said, no. I want a graphical approach that'll get me the shear and moment diagram for the whole beam. Remember that? We're going to construct a similar graphical approach to construct influence lines, but the way that we do that is going to be a little wild, okay? Now, I do say for indeterminate structures, you may have a nonlinear influence line. I'll show you a note on indeterminate influence lines a lot later. But for determinate structures, always lines. Now, how do we prove this? Or more specifically, how about this? Can we develop an approach to draw influence lines for any arbitrary structure? So, like, what I'm getting at is if I wanted to draw the influence line for this, I feel like what I'd have to do up until now is write myself a little table. Like if I'm interested in the reaction at B, put the load here, get an answer. 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 That's kind of tedious, right? I want something that's a little more straightforward. Is there a more elegant approach? Yes, there is, and it's called the Muller-Breslau principle. Okay. Now, the Muller-Breslau principle takes a little bit of time to digest. Okay, but I'm going to read the Muller-Breslau principle in its entirety, and then I'm going to describe how it works. Okay. So here's the Muller-Breslau principle. Okay. What is the principle, by the way? What is the Muller-Breslau principle? It is a graphical approach for drawing influence lines. What does it say? So I'm going to read it out verbatim. The deflected structure, or the deflected shape of a structure, represents, to some scale, the influence line for a force effect if the quantity in question is moved through a small unit displacement. And I get it. That's word salad. Okay? All right. What does that mean? Okay, what that means is the following. If I want to construct an influence line, what I do is this. I take the structure and I identify that response. Remember, like the reaction, the shearing moment at a particular point, etc. I then remove from the structure the ability to resist that response. Okay? I then take the structure and I move it through a unit displacement, okay? And the resulting deflected shape is the influence line. I see a lot of you writing this down. I'm going to give you a set to write this down, and then we're going to talk about it. Oh, sorry. I didn't hit the button there. All right. Everybody with me so far? Okay, so I want to look at this beam here, okay, and I want to go through the Muller-Breslau principle, and I want to see if I can apply the Muller-Breslau principle as it's written here to draw an influence line. Okay, so what does the Muller-Breslau principle say? It says identify a response of interest. So let's say we're considering AY, okay? So we're considering AY. And it says remove from the structure the ability to resist that response. So what that means for a support reaction, so I'm just going to get rid of that support reaction. Now, in your mind's eye, let me ask you a question. If I have a beam and this is Sparta kick that support out, what happens to the beam? Ooh, just falls down, right? Everybody with me on that? So what happens then if I take this point and I move it up one? If I move it up one, what does the beam look like? It lifts up and it does that, right? The beam just lifts up. Doesn't this look like the influence line? That is the influence line for the reaction at A, okay? That is a very quick means that you can use to determine the influence line by removing from the structure the ability to resist that response and then moving the structure through a unit deformation, okay? Let me show you an example that's a little bit more complicated, okay? So let's take a look at this one and look at me with my high-tech, like, demo right here. Very high-tech, I know. But I've got a beam that has 3 supports, and I put a hinge right here, okay? All right, so let's make sure. Okay. Now, okay, let's look at some tips and some rules for drawing influence lines for reactions, okay? So what I'm going to do is I'm going to take some structures, and I'm going to draw the influence lines for all the reactions, okay? So this structure has 3 reactions, A, B, and C, and let's assume that I have drawn the influence lines for all of them. What are some characteristics of all of these influence lines that should be true, okay? Well, the first thing that should be true is that the influence lines should equal 1 at the reaction of interest and 0 at all other reactions. Now, does that make sense? Well, think about it. If I put a load right here, what's the reaction at A? And what's the reaction everywhere else? 0. What if I put the load right here? The reaction is 1 at B and 0 everywhere else. What if I put the reaction at C? The reaction is 1 at C and 0 everywhere else. So that's got to make sense, right? What about else? They're always linear. They're always linear, okay? Now the third, and this is where, I think this is probably the one that causes the most issue, is that hinges serve to change the direction, okay? So let me show you something. Okay, so let's take this beam, okay? Let's start off with the reaction at A. Okay, here's A, B, and C. So let's look at the reaction at A. So everybody watch this up here, okay? So what I'm going to do is I'm going to remove from the structure the ability to resist this reaction. So I'm just going to take this pin out. And what I'm going to do is I'm going to move this point through unit displacement. I'm going to pick it up. Watch what happens over here. So I'm going to pick it up. See what happens? See how this went up? See how this went down and then it kinked back up? Y'all see that? Okay. Okay, so let's do point B. So if I do point B and I lift B up, see what the hinge did? See how it kinked the direction? This is all a straight line, this is all a straight line. What about point C? Okay, so we'll take point C out. Now if I lift point C, what's going to happen? Let's just see if everybody pays attention. What's going to happen? What's that? All right.
Well, it wouldn't do anything because it's kind of pinned down at A.
Well, this part's pinned, right? If I lift this up, this is just going to stay there, right? Because this segment has got a support here and a support here. So if I lift it, this beam over here, this beam on this side is just sitting there, right? So if I look at the resulting influence lines, here's what I've got, right? So here's the influence line for the reaction C. So what happened? It's just that part that went up, right? So if I do the influence line for the reaction at B, so the influence line for the reaction at B, so what happens is I lift point B up, right? So point B goes up to 1, but this one goes a little higher because this is all one straight line segment, right? So if one way of thinking about it when you're drawing influence lines for reactions, dropping my pens, influence lines for reactions, is just take a look at the beam. How many solid links are in the beam? And I propose there's 2 because there's a hinge in the middle. So that means that there's 1, 2 line segments, 1, 2 line segments, 1, 2 line segments. Make sense? What else? Look at the reaction, the influence line for the reaction at A. 1 here, 0 here, 0 here. What about for B? 0, 1, 0. What about C? 0, 0, 1. Make sense? Everybody with me on that? You want me to blow your mind once more? Watch this. The definition of an influence line says that we are moving a load that is how much? 1, right? And it's 1 going down, right? What's this value plus this value plus this value? What's that plus that plus that? What about that plus that plus that? What about that plus that plus that? Positive 1. The reactions all have to sum up to 1 going up because there is a single unit load going down. Sum of forces in the y direction has to be 0. So that's another check, that at every point, the sum of your influence line for reactions must be equal to 1. Make sense? Let's do some problems. Okay, so I want to explain my naming here. So I have influence line 1A and influence line 2A because we're going to come back to these problems on Monday and do influence line 1B, influence line 2B. So the same problem, we're just going to do them differently. And for the beams shown, I'm going to draw the influence line for the reactions. Okay, so let's work through this. Now I will warn you that I've done this weird stretchy thing with the beam where I've stretched it out, so it's kind of stretched this way. But I did that because I didn't want the line to be cramped. I wanted it to be very visible what I was doing. So my influence lines may, or the original beams might look a little stretchy. So, okay. Okay, so what I'm going to do is, again, like I said, they're not shear diagrams or moment diagrams, but I know you see this and you're like, I don't know, Dr. Mike, it's looking a lot like it. Okay, so let's draw the influence line for AY. Now, how many solid segments are in the beam? Like the last beam had 2 because there was that hinge. How many solid segments are in this beam? 1. So that means the influence line should be a single line, okay? Now, can anybody sort of like describe to me what it's going to look like? Anybody give it a shot? Mr. Bacon.
Up at 1.
1 here.
Yeah. And then go down linearly till it's 0 at C.
So over here it's going to be negative, right?
Yeah.
Okay. So what you're saying is that the influence line is going to look like that.
Right.
That's correct. This is the influence line for the reaction at A. Okay, well, we're going to come up with some values here. Okay? So this is 1 and this is 0. Okay? Would everybody agree with that? Okay? So what is this value? 1/3. Okay? That is correct, but how did you get that?
Because it is 1/3 from C and 2/3 from A.
Exactly. So what you can do is you can say, okay, you can say we'll call let's come up with some symbols. We'll call this H1, we'll call this H2, and we can say 1 is to 30 as H1 is to 10. Right? And this is, if that's 1/3, what's that one going to be? Negative 1/3. Okay. Does that make sense? Okay. All right. If that makes sense, let's see. Let's see if we can do the influence line for BY. All right. Now, how many reactions do we have on the beam total? Vertical reactions. 2, right? So if we've got 2, we already have this influence line drawn. We should be able to reference it to make sure the values are right on the next one. For example, what should the value be right here?
0.
What should the value be right here?
2/3.
How about right here?
1.
How about right here?
1 1/3.
Exactly. And how are you doing that? Because the sum has to be 1, right? But let's also, so let's do that. So let's do that. Third. Okay. Now, a couple things I want to ask are, do these plots conform to the Muller-Breslau principle? So, for example, if I have this beam and I kick out that roller, let's say at C, and I take C and I lift it up 1, does this line look like the deflected shape? Yeah, it does, right? Same thing with A. If I kick out the support at A and I lift it up, point C's don't act like a pivot, sort of like a seesaw, right? Point C is the fulcrum on the seesaw, right? So it lifts up, everything to the left of A goes up, everything to the left of C goes up, everything to the right of the C goes down. Make sense? Now, does this conform to statics? Let's check that. So let's do this. Let's consider the load at point B. Okay, so what I'm getting at is I have a beam like this. I have this, and we put the load right here. So like a 1 kip load, right? So this is AY, this is CY, this is 30 feet, this is 10 feet. Does that make sense? Let's see what happens. Let's sum moments at A. So what do I get? I get 1 times 40, and that has to be balanced by CY times 30. So CY has to go up. So 1 times 40 has to be balanced by CY times 30. So CY is positive 4/3. And then if I sum forces in the Y direction, I have CY is 4/3 going up, and I have 1 going down. I got to have more going down. How much do I have to have going down? AY. And AY, so if 4/3 is AY plus 1, then AY is 1/3 down, right? And so what did we get when the load is at D? We got BY is positive 4/3, AY is negative 1/3 because AY is going down. Does that make sense? Everybody with me so far? So let me ask you a question. Let's talk about applications of the influence line. This influence line will tell you the reaction at B. Let's just look at this one. This influence line will tell you the reaction at B for a unit load anywhere on the structure. So let me ask you a question. How would I determine the reaction at B? Look, let's just consider a problem. How would I determine the reaction at B if I told you that this was the problem? How would you get the reaction, or sorry, the reaction at B? I'm saying B, this is C. I'm sorry. That's C. How would I determine the reaction at C if I put a 45 kip load right there? How would you do it? What's that? That's how you would do it before. I'm asking how you would do it now. I'm take 45, multiply by whatever it is right here. Do you see what I mean? Here's my point. If I put, okay, let's do this. Okay? Let's do this. If I put a load right here of 1.0, I propose the reaction at C is 2/3, right? So if the reaction at C is 2/3 when the load is 1, what is the reaction at C when this is 45 kips? It's 45 kips times 2/3, right? So I propose to you that I could get the reaction due to any load anywhere by just taking the loads times the values on the influence line. Does that make sense? that is a new way of analyzing structures, is to use the influence line directly, okay? But the other thing that the influence line tells you, and I want to get into my next example so I don't want to go too long, is it tells you where to put the load. For example, if I'm designing the foundation under support C, where should I put my moving loads? Maybe right here. Because loads over here are going to generate the worst reaction at C. And how did I figure that out? That's the biggest value on the influence line. Make sense? So we can use it directly for analysis and we can use it directly for design. It's an incredibly powerful tool. Okay? Let's do one that's a little more complicated. Does anybody have any questions on this? Okay. Let's look at this one. This one's got a little bit more going on. Okay? This one is a little bit more like this one, only it's kind of flipped. I have support A, support B, support C. Now, one thing I'll mention, I have this section 1-1 right here. We are going to look at section 1-1 later. We're going to be drawing shear and moment influence lines for that point later. Okay? But right now, I just want to draw our 3 influence lines. And we'll draw my nice little guides. We'll do one at every point. Now that last example, I kept saying support at B and support at C. There was only 2 supports. My apologies for that. All right, so let's start right here. By the way, what physical tool do you think would help you on homeworks and exams when you're constructing influence lines? Maybe a straight edge? Take a ruler or a straight edge to the last exam. Okay. Let's draw the influence line for the reaction at A. So before we do any drawing, let's do some value assessment. What's the value here? What's the value here? What's the value here? Before you draw anything, that's just basic common sense structural analysis. The reaction's got to be 1, or the influence line's got to be 1 at the support of interest, 0 everywhere else. Everywhere else. Ugh, I'm getting tongue-tied today. So, all right. Now, considering the presence of the internal hinge, can somebody tell me what they think the influence line is going to look like for the reaction at A? If I kick the support out of A and move it through a unit displacement.
It's going to go down to 0 at the hinge and then be 0 everywhere.
That is 100% right. We consider this as a rigid segment because we don't have any curved lines. Influence lines are straight. So if we lift this up, it pivots at the hinge, but I've got this segment right here pinned down at B and C. So what does my influence line look like for the reaction at A? It looks like that. That's 0. That's 0. Influence line for the reaction at A. Done. So it's a very interesting result. I posit to you that for this beam, let's draw the beam right here. So I have a hinge right here. I have a support right here, support right here, support right here, right? Is that what the beam looks like? What this influence line is telling me is I can put a ridiculous amount of load right here. I can put all sorts of loads right here, all sorts of loads right here, and I propose to you that the vertical reaction here is 0. Because the influence line tells me that if I ever put loads anywhere from here to here, it generates no vertical reaction here. The vertical reaction here is 0. It's kind of crazy, isn't it? All we had to do was draw an influence line. Didn't need to do any statics. And I propose to you that for this beam, AY is 0. No analysis. No math. Or analysis, but no math. Let's do the influence line for the reaction at B. Okay. So somebody else. Mr. Miller, help me out. So, first off, what's the value here?
0.
What about here?
1.
Here.
0.
Okay, so 0, 1, 0. All right, so we know that's, so we know we got to come back to 0 right there. This has got to be 1. This has got to be 0. So, if I kick out that roller and I pick it up, what happens?
It goes to a peak at the hinge.
It goes to a peak at the hinge, so we've got a straight line going like that, and then like that. So, maybe what I'll do is I will, just to make sure the art looks good, I'm going to erase this. And what it's going to do is it's going to go like this, and it's going to go like this. And this value is 1. Okay? Okay. So I would like, for the sake of discussion, to figure out some intermediate values. Can somebody tell me how to find this value, this little one over here on the right? How do we find that value? Well, let's look at this triangle. This height is 1. What is this width?
20.
So if this is 1 to 20, what is that right there? We'll call, let's do this. Let's come up with some symbols. Let's call this H1. Let's do H2. So we're doing H2 first. So 1 is to 20 as H2 is to what? 6. So therefore, H2 is 6 over 20, or 3 over 10, right? So H2 is 0.3. So I'm just curious, if this is 0.3, can anybody eyeball this? Anybody tell me what H1 is? Anybody have an idea? That's 100% right. Because what we're doing is we're saying 1 is to 20 as H1 is to 28. So H1 is 28 over 20, or 14 over 10. This is 1.4. I'm sure there's some math professor out there who's like, no, it's supposed to be 7 over 5. Okay, 7 over 5, I still wrote 1.4. Let's see. Let me move this down. So I'm actually, I copied the image because I'm going to use it on Monday. So I copied it again. Let me give myself a little bit more space on the guidelines. Okay, so let's do this. Now the last influence line should be the easiest, because what you should be able to do is just reference all the ones above it and make sure that the plot makes sense. Let's start from left to right. What should this value be?
0.
What about this one?
Negative 0.4.
-0.4. What about this one?
0.
What about this one?
0.7.
0.7. And this one?
1.
1. So what it should look like is, give me a little bit more space here. So it should be 0, negative 0.4, 0, 0.7, and 1. So it should go like this. It should go like that. So this is 0.71. Okay? And does that make sense from a structural perspective? If I remove this roller and I pick this up, again, so it's sort of like this, right? So if I remove this and I pick this up, what happened? Right? See what happened? So how it went down like that? Went down, kinked at the hinge, went back up. Does that make sense? Told you today's different, isn't it? Feels different. It's a different topic. It's unique. But to me, this is where structural analysis really gets real, and you really get to make some real insights into how structures behave. I mean, like, again, like, go back to this original example. If I were to remove this, I posit to you that the vertical reaction here is 0. Because all I have to do is lift that point up and see that the only way I get a value here is if I have load on this end. If I don't have any load on that end, the reaction's 0. Really cool stuff. I think this is really fun. All right, let me stop for a second and see if anybody has any questions. You think if I gave you a couple to do on your own, you could do? So the thing about influence line homeworks is that they're usually really short. Like, they don't take a lot of work, but sometimes you end up staring at the page a little bit longer. What's this thing supposed to look like? But think about it, you know, think through it, and I think you can figure it out. Okay, so let me explain what we're going to do next. Okay, so next what we're going to do is this. I mean, this is influence line for reactions. What we're then going to do, what we're going to do next, is we're going to look at what does the influence line for shear and moment look like. Now, the way that it works is we have to draw the influence line for shear and moment at a point. It's not for the whole beam. So we're going to draw like the influence line for shear here, the influence line for moment here, or maybe the influence line for shear and moment both at the same location. Okay? And there is a very particular way that we do that. How do we do it? It's the same thing with Muller-Breslau principle. We remove from the structure the ability to resist that response at the point of entrance, or the point of interest. We then move the structure through a unit displacement. How we move the structure through the displacement is a little unique. With beams, or with moment, we have to put it through a unit rotation. For shear, we have to put it through a unit shear displacement. So there's particular ways of doing that. So we're going to talk about that on Monday. But I think you'll find this is a very interesting topic, but there's a lot of really cool applications of it. I'm going to pull up the code one more time in case anybody missed it, and I will see you all on Monday.